Today, we're going to peel back the curtain on the core technology that powers so much of modern AI. We're going inside the digital minds we call neural networks, and what we find might just surprise you.
I mean, you've used them, you've seen them, but how do they actually work? How does a machine learn to recognize your face or even write a poem? That's the central mystery we're going to unravel right now.
Well, the answer lies in something called an artificial neural network, or ANN for short. And yeah, as the name suggests, the original inspiration for this incredibly powerful technology is the most complex machine we know of, the human brain itself.
But what's actually inside this digital brain? Let's break down its fundamental components.
Now, the core idea here is just fascinating. Intelligence in a neural network isn't born from one giant complex calculation. No. Instead, it kind of emerges from the collective behavior of thousands or even millions of tiny, simple units all working together in layers. Each little neuron just does a very small job, but together they can achieve something incredible.
To really get a handle on how these layers work together, let's use an analogy. Think of a neural network as a factory assembly line, but instead of building a car, it's building information.
So raw data, like the pixels of an image, enters at step one. The first layer of neurons gets to work, but it's only looking for the simplest possible things, like basic edges or little curves. The output from that layer then gets passed to the next, which combines those simple edges into more complex shapes. Each layer builds on the last, turning simple data into an increasingly abstract and useful understanding, until finally that last layer makes a decision.
That assembly line analogy gives us the big picture, right? But let's make it more concrete. We'll use a classic task for a neural network, learning to recognize a handwritten number.
The input data is simple enough. It's a picture of a handwritten 9. The network has one job: figure out what number this is.
So the first layer gets the image. It doesn't see a 9. It doesn't even see a circle or a line. It sees the most basic components you can imagine: individual short strokes, tiny curves, and raw edges. That's it. Okay, now the output from that first layer gets passed along. The next layer looks at all those simple little strokes and curves and starts to piece them together. And this is where the magic starts to happen. Certain neurons in this layer might activate, essentially saying, hey, I see a pattern that looks like a loop, while others might pipe up with, I see a pattern that looks like a vertical line.
And then finally, the output from that layer goes to the last one. This final layer takes the assembled patterns, the loop and the vertical line, puts them together in the right arrangement, and makes its final conclusion. The pattern of a loop on top of a line means the answer is 9. Simple as that.
Okay, that makes sense. But it begs a huge question, right? How does the network know that a loop and a line equals a 9 in the first place? How does it get so smart?
Well, the crucial point is this. The network learns by adjusting the strength of the connections between its neurons. A great way to think of these connections is like a million little volume knobs. During training, the network is basically trying to figure out how much to turn up or turn down every single one of those knobs so that when it sees a 9, the 9 neuron at the very end lights up the brightest.
Here's another helpful way to think about it. Imagine the network is a student taking a test with thousands of questions. In this case, thousands of pictures of numbers. At first, it's just guessing, and it gets almost everything wrong.
When the network gets an answer wrong, it gets feedback. A process called backpropagation kicks in. It's kind of like a teacher telling the student not just that their answer was wrong, but also helping them trace back their logic to see exactly where they made the mistake. The network uses that error to go backward, layer by layer, and slightly tweak all those little connection knobs so it's a tiny bit less wrong the next time. Now repeat that millions of times, and pretty soon, your student becomes an expert.
Now, with all this talk of brains and learning and students, it's really easy to get carried away. That's why it's so crucial to ground ourselves in reality and remember what these networks truly are.
You know, while the brain analogy is a fantastic starting point, it definitely has its limits. An ANN is fundamentally a mathematical model, a very, very complex one, but it's math nonetheless. It doesn't have consciousness or understanding. What it is, however, is an unbelievably powerful tool for finding patterns in data, patterns far beyond what a human could ever program by hand.
And that's why this all matters so much. This core technology is what allows your phone to recognize your face. It's what allows ChatGPT to understand your question and spit out a coherent answer. This layered, pattern-finding approach is the engine driving so many of the AI breakthroughs we see every single day.
So, to sum it all up, neural networks are mathematical systems, inspired by the brain.
They process information in layers, building this complex understanding from really simple parts. They learn by practicing over and over again, adjusting their internal connections based on feedback. And it's this elegant layered design that lets them tackle some of the hardest problems in AI.
And that leaves us with a final, really important thought. If these powerful systems learn everything they know, their skills, their abilities, their entire worldview from the data we give them, well, it forces us to think very carefully about the patterns we're asking them to learn. What does that data truly represent? And what kind of intelligence are we actually building as a result?